until we get more people. But meanwhile, does anybody have any comments to say or questions or things that they would like to have discussed today? Or news items or anything you want to say? Has anybody tried that machine learning.ai class that started on Monday?
Yeah, I'm participating in that.
Yeah, that was.
I actually did it earlier. Go ahead.
Yeah, go ahead. Go ahead.
I actually did it earlier this year, and I was going to do it again to see if I could perform better. The
Sounds
Slack,
good.
the Slack channel is pretty chaotic.
I see. Yeah, I know. I was looking at that. I'm in the class. I haven't done the assignment, but I know it's due. It's probably due now because they're in Europe and it's due on September 7th. And I don't know, but I guess I'll try. I'm not going to give up. I'm going to try to hang in there and get it done, even if I don't get credit for it.
I think you have until the 15th.
Oh, I thought it was the 7th.
No, I think you have until the 15th.
Oh, great. I'm saved. Okay.
Yeah, it's every 2 weeks. I think he's gonna release the assignment every week. Yes. However, you'll have like 2 weeks to submit. I attended the session 0 this morning.
Yes, I meant to, but I was sleeping. So
yeah, well, like there wasn't much. He just gone through the resources, how it's gonna go proceed. I don't think it's going to be like every Saturday morning. So it's probably just the website and the Slack channel. Mm-hmm. What he covered in a nutshell today is just a walkthrough of different portion of a website. So if you just go to I think mlcodes.ai, if you look at the resources, the roadmap, if you go through them, it will make sense. And that's all he covered.
That's great. That's really helpful, Dinesh. Yeah. So I'm going to definitely try to definitely get involved with that. Some reason it just got away from me because I started listening in on these code walkthroughs that Jeremy's having every day on the version 2. They're getting ready to release it, but there's no release date yet. But he's walking through pieces of the version 2, and it's really useful. It wouldn't have been useful to me had I not struggled with these notebooks in this class and got to the point where I can sort of understand what he's doing. But yeah, it's really interesting to see what's planned in version 2.
Yeah, well, I attended first 2 lessons just a code walkthrough because that suited in the evening time for me.
I
couldn't make it much, but that there is a reason because I haven't done this one. I haven't been practicing too much of these ones. So it makes sense because you have been practicing and then it makes sense to you. But I think it sounded lots of changes and lots of software engineering he has introduced.
Yes. He's really excited about that. He seems like he wants to write his own language. In other words, he's not satisfied with how Python works, so he's building his own version of Python or the Python parts that apply to Fast.ai. So it's really interesting to watch how he works and how he and his team work. And you do learn. It is heavy on software engineering, and it takes a lot of. Listening to the code walkthroughs is not enough. You really have to, and I still have to do this. You have to go through and read it yourself and look at the discussions on forum and all that. It takes a lot of time. But that's the problem with. There's so many things out there.
Yeah.
It's like a candy store out there. There's so many things, and you want to do all of them, but
True.
Not productive to do lots of things and just scratch the surface. It's much better to dive deeply into 1 or 2 things and just ignore everything else for a while until you get these things done. So
Yeah, and couple of points which Jeremy made, that somewhat V2 is going to be a little bit more stabler, so he wouldn't be changing, making a drastic changes going forward, because I think he is writing a book. So both API book need to be aligned, but he wasn't like 100% committed. So that's one thing. Another thing he mentioned is, interestingly, this that the code rewrite is somewhat influenced by the Swift for TensorFlow. So whatever they are doing on the other side, so he has a knowledge what's going on over there. So he's improving bits and pieces here, keeping that in mind.
I see. Yeah, that's a good point to bring up. They are coming out with a book on OReilly, it's going to be one of the OReilly series. And so, and he did say that this version is going to be more stable, because a lot of people complain that Fast.ai is so rapidly changing that no sooner did they get used to one construct, then he's already destroyed it and put something else in its place. And you can see that in this class even, where he builds stuff and then he says, okay, now we're just gonna do something else. And then you got used to doing something one way, building a runner or whatever, and then all of a sudden, oh, we're not going to use this anymore. We're not going to use this. And so it is kind of fast and fast moving. So I can understand that.
Yeah. Just out of curiosity, you mentioned about the Fast.ai team. I thought there are only two people, Jeremy and then what's the other name? How do you pronounce? Sylvain.
Yeah, and that's essentially the main team, but there's a number of people helping out on the development side, where they'll make what do you call PRs? I forget what a PR is. The suggestion for a change to the code, and then they'll carry it out if Jeremy and Sylvain agree. So yeah.
Yeah. So interestingly, like I was just curious, is anybody from this
Joseph PR, right?
Yeah, PR.
Pull request.
A pull request. That's right. Yeah. That's right. So somebody has an idea to improve the code, then they put up a pull request, and then Sylvain and Jeremy have to look at it and have to agree, yes, do this, and then they'll go and do it, and they'll actually merge that into the Fast.ai library. So there's a number of people doing that as in addition to Jeremy and Sylvain. Yeah.
Yeah, and I was just curious, is anybody from this study group made any pull requests so far?
Oh yeah, I tried once, cause that was last year, but the problem was that I've been developing with Python for a long time, but the code base for Fast.ai is not really Pythonic. Like, it's weird.
Yeah.
Like he mentioned it too, like they write their own code in a very, really tough way that I don't understand. Like their class and methods, the way they arrange their packages and their code structure. So it was really hard for me to wrap my head around it and to submit a pull request. Even sometimes when I try to go through the code base and try to see what's going, because at a point in time when I was taking the version 1 of the Fast.ai lesson, there was a time I was having issues with the data bunch method, and I tried to go to the code base to figure it out. I was lost, like I was literally lost. So the library is good, but making contributions to Fast.ai is kind of like tough, because their code structure does not follow some PEP standard, and you just do things your own way, and it's tough for me.
Well, I have an idea that the more we get used to this way of doing things, the more that we delve into these classes. And of course, every time my plan is that every time he runs the class again, even version 1, even course 1, I'm going to try to follow it, because every time they run the class, they change something. And and my thinking is that and I've been following this for almost a year now. I think the more you get used to it, the more time you put in, the more you'll get used to speaking their language, the way they do things. And then my goal is eventually to try to help contribute to the code base, but I'm not there yet. So.
I like Fast.ai for what it does and how it abstracts a lot of things, but I think I don't like it because you use something today and then tomorrow it's broken.
Yes,
I mean, and
yes.
and then you like run the code and then the whole thing like, and if you want to debug it, and you gotta go through hell, and then you gotta wait for a new update, and like, so I mean, if only that, you know, there should be like someone like backward compatibility, or put into consideration that most people are actively using this right now, even in like real life project. Because when I was using it, I was trying to, I was doing something because I'm in medical school. So I was trying to build something for the pathologist here in medical school. And I had my demo and I had to make a few changes to my code base. And then in the morning, I was trying to run it and then nothing was working. I mean, it fell over. So it became a huge problem. I like what they're doing, but I mean, Fast AI needs to like make it easy for someone to not worry about the fact that my code might break, because like every week something changes. The next week, I mean, it's a new name, or the method has no name, or something like that. I mean,
yeah, and I think that as Dinesh said, that the new version 2, is their goal is to make it more stable, so that their goal is to actually finish it. I think Jeremy, I think the sense is that he wants to finish it and put out a sort of a final stable version that everyone can then use, and that's why he's writing this. That's why they're writing this book. So I think that problem with Fast AI is going to eventually sort itself out. It will become more stable, and you'll be able to depend on it to build whatever you're building.
Yeah, okay. I have a question, Alexander, for you with regard to the pull request. So how does it work, in a sense that you find some bug or want to add some functionality? Do you make changes into your local code and then test it, and then once you're happy, then you ask them for a pull request, or other way around?
Okay, so this is what you do. Like, pull requests are standard things to do when the code is an open source code, right? Like when you pull the code down and then you see something you want to make a change to, or maybe you saw, okay, usually there are issues that are listed, right? Like if you've worked in open source before, you'd see in the gist, you'd see things marked as issues, right? And then you decide that you want to fix it, right? And then you pull the code down locally to like in your local computer, and then you write the code, and then you think it works, right? You are not allowed to push that code back to the master repository, or you're going to break something.
Correct.
Right? So usually I'm going to use a term called like a sandbox. So you're going to push the code to a branch, you know, and then when you push the code to a dev branch, you're going to ask for a pull request. Like a pull request is when the repository master looks at the code base and then looks at what you have done and make sure that it follows what they want to do, and then it obeys all the standards based on their, because usually every code base has like an outline on how you should contribute to them, or what you should do and what you should not do, probably how they name their classes, their methods and functions, whether they use 4 spaces or 2 spaces. So the person is going to like review all this thing and then say, okay, cool, this matches what we want, and this code works. And then they look at the standard of the code and how much the craftsmanship in the code, whether it, not really, because most time for open source code, it's not really about whether it's working. There are a lot of considerations that they put into place to know, okay, yeah, we should merge this code. So when you submit a pull request, it's more like asking, hey, I've done this thing, can you look at it and tell me if it's good? If it's good, can you just like merge it to the master code? Okay. So when they look at it and then it works for them, they're going to merge it to the master code base, and that means it's available to everyone. Yeah, it's like a pull request.
Yeah, makes sense.
For that, that's a great description, Alexander.
Absolutely, thanks.
Yeah, okay, so let's get started. Now that we have about 15 people, that's good enough to start. So my plan was to, I know I didn't finish the 05B notebook, and I wondered if there were any questions about that before we start the 06 notebook. Okay, I'm going to, I'll just have a look at overview. I always mean to put together a nice package of slides, but I never get around to it. So I'm just going to go over, today's plan is just to go over the notebooks 6 and 7, and I suspect we're probably not going to get through 7. And then next week to finish, start the chapter 11. So, but I have a feeling that we'll still have a little bit of chapter 10 to finish next week, but we'll see. We'll see how it goes. So I'm going to get started with the lesson, with the notebook number 6. I'm going to stop sharing this PowerPoint, get to the notebook. So here we go. Sharing. Is everybody seeing the notebook 6?
Yes, I can see it.
Yeah.
Okay, everybody? Okay,
I
great.
can.
Super. Let's get started. By the way, I found out I had been writing these notebooks and reworking them and so on, and I finally got to where in notebook 5, my revisions started to break. So I still have some fixing to do. So for today, I actually started all over again using all of the original notebooks, and exporting and importing everything. So today's number 6 notebook is basically the same as, except for a few comments, it's basically the same as theirs, as the original Fast.ai. And I'm using all the previous original notebooks too in my export, in this first line where you import everything. So I ran everything from the original notebooks, reran everything, and then imported that, just so you know. Because I think there's something in my notebooks that's broken, and I still have to fix it. So I'll be working on that. Anyway, so we'll get started. We'll import everything up to the last notebook. And the first thing that they do is they get the data. Then he has this helper function to normalize the data. Remember, normalizing means dividing the data by its, subtracting the mean from the data and then dividing by the standard deviation. If you remember that. And so he builds this normalized function where he gets the mean and standard deviation, and then it's sort of this normalized to function, that is, where he gets the, and what we mean by that is we're normalizing to the training set. And so he gets the mean and standard deviation of the training set, and then you return the normalized version of the training set and the normalized version of the validation set. And remember, we had this function normalized. I think we built it from before, and the normalized function subtracts the mean, divides by the standard deviation. And the mean and standard deviation are passed in. And so notice that we've got the mean and standard deviation of the training data set, and we're passing that into the normalize of the to this function, normalize train. But notice that we're normalizing the validation set by the same mean and standard deviation. That is, we're normalizing the validation set with the mean and using the mean and standard deviation of the training set. Now, this is standard practice, and that's because the training set is your known data, and your validation set is you're pretending like you don't know what the mean and standard deviation is should be. So anyway, so that's our little helper function, and he exports it for later use. So now we're going to run this actually. We're going to actually replace the training set and the validation set by the normalized versions. Then we're going to build a data set object with these guys. Remember that the data set object has, we could actually look it up. We can look this up. So we'll do this. The main thing about the data set object is that it has properties X and Y, so that you can ask for, so you get this data set, and you can ask, so train ds, valid ds is the output, and you can say train ds.x, and that gives you all of the, for example, in the MNIST data set, that gives you all of the data pieces, that is the digit arrays, and train ds.y gives you the labels for it. So the main thing about this data set object is that it has properties .x and .y, which allow you to get at the training part, the data part, that is the MNIST digit data, and the labels part, the .y is the labels part. So that's the data set. And remember this, this is really useful to put this double question mark in front of a function or an object, and it gives you a lot of information about it. Some cases you even get the source code. So this is very useful. Now he says, let's check that it behaved properly. What do we mean by that? Well, once you've normalized the data set, it should have a mean of 0 and a standard deviation of 1. That's what that means. And so let's try it. And we find that, yes, the mean is very close to 0, and the standard deviation is very close to, is actually 1. Oh, and the other thing is that it, somewhere in here, it builds tensors out of all of the outputs come in tensor form, which what we need later. Now I added this extra line because I like to check to see what happened, what are the mean of the validation set, what are the mean and standard deviation of the validation set. They don't have to be close to 0 and 1, but it would be nice if they were. So let's just check that, what happens. And they're, again, they're close to 0, not as close as the training set, and close to 1, not as close as the training set. So that's good, that's just a good check. Okay, so the next thing he does is, remember this, I'm going back to his notation because I tried, when I was rewriting the code, my goal was to replace all these cryptic variable names with names that I can understand and that you can understand. But since I'm going back to the originals, I'm going back to these cryptic names that they seem to like in Fast.ai. So we have NH, remember that's the number of hidden layers, and BS is batch size, so we're setting number of hidden to 50 and batch size to 512. Remember their C is basically the number of digit classes, so it's going to be 10. And then here we define the loss function, and then we build a data bunch. And remember, the data bunch takes these data set objects and makes them into data loaders. And remember that a data loader is an iterable that returns a batch every time you call it. It returns a single batch. So so now we're going to put the data into a data bunch, which is really cool little object because it allows you to get out batches. So the inputs are the data set objects, train DS and valid DS, the batch size, and the number of outputs. And now we have a data bunch object.
Yes. Joseph, quick question. Yes. What's this get star get DLS?
Yeah, get DLS is a function that gets the data loaders. It was developed in one of the previous notebooks. But what it does is it takes the data set objects that we built here.
Yeah.
These things. It takes these as inputs, and from them it generates this these data loaders, which are iterables. And so what this function does, get DLs, is it outputs a data loader for the training set and a data loader for the validation set. And that, when you go back to see, well, let's see that. Let's see if we can.
Okay, I think I got the idea. What this star stands for? Like,
yeah,
why do?
Yeah, I'll get to that in a sec. I want to demonstrate here. Let's ask for what does this data loader function look like. Oops, get DLs. Yeah, there it is. No docstring. So it returns. You see, it returns a data loader for the training set. It's a tuple, a tuple. It returns the first element of the tuple is the data loader for the training set, and the second element is the data loader for the validation set, right?
Yeah.
So Dinesh, to your question, the star basically iterates through both of these. In other words, it forces both of these things because get DLs has two outputs. So the star forces you to iterate through that list, through both of those. In other words, the data loader for the training set and the data loader for the validation set, right?
Yeah, so this is iterating number of times C?
No, it's star basically says, okay, if you give it an input that that's a tuple, right? And that's what this is. The output of this function, get DLs, is a tuple. And
Correct.
it has two elements, and the first one is the training data loader, and the second element is the validation data loader.
Yeah.
So the star in front of this thing means get both of the elements of the tuple.
Okay.
Okay. Okay. And that's what the data bunch needs. It needs both data loaders as its inputs. So this is just, the star just forces it to go through both, to include both pieces of the tuple. And if it was a list with 10 elements, then the star means include all of the elements. That's what that star means.
Okay. Okay. And then what the C, so data bunch is getting C as well, as in a second input.
Yeah, the C tells it the number of outputs that it needs to make.
Okay.
Because remember, C is the number of digits. So yeah, so C is the number of label, C is actually this, what do you call it? The cardinality of the label set. It has 10 possible values.
Yeah, the target class. Yeah.
Yes, that's right. That's right.
Yeah. Okay. Thanks.
So yeah. All right. So next, so then he says he wants to refactor the layers of our convolutional neural network, which is coming up. But he says he needs this little helper function. Did we already build? Let's see. Yeah, we're just starting to build. We haven't built the convolutional net yet, but he builds before we start. He's building this. He's making this little helper function, which it's a class. It inherits from the nn.module class. Remember, in the nn.module class has all the layers and stuff like that. Maybe it would be helpful to take a look at that for a minute. It has a lot of documentation, I think, but let's have a look. There it is. So this is the base class in Fast.ai and in PyTorch, I believe. I believe this is from PyTorch, and it's the basic thing, the basic construct that you use to build your neural networks, right? And so it has a forward method. It has an init. It has a lot of methods that are useful when we build convolutional neural networks. This is all, Jeremy didn't build this. I believe this is directly from PyTorch. So anyway, so our lambda function is going to inherit from the nn.module class, and that's what this super.init means. It means initialize from the parent class, and the input is going to be a function, and the forward method is just going to be to apply that function to the input x. And then so that's this class. And then, he includes that in XWorks. So this means that it's going to be useful in our future notebooks. Anything that says sharp export like this, that is going to be used in all the future notebooks. So pay attention to those things. So this is kind of like he's building something that he wants to use again and again. And the second piece in this is this little function called flatten, which you kind of have an idea what it does. Is it takes an array and flattens it out to one dimension. So f.shape of 0 is going to be the length of the batch, and the -1. See, I'm not sure what the -1 does, but the result is that it takes an array and flattens it out into a vector. So that's this function. And then this one, I was wondering why he didn't include this second function, which kind of does the reverse of flatten. So it's called mnist resize, and it returns, it takes the mnist data, which is provided in the form of one-dimensional arrays. Remember, the mnist data, each item in the mnist data is a 784 length vector, which is really a 28 by 28 array that's been flattened, because 28 times 28 is 784. So this mnist resize does the reverse. It takes the vector and returns the actual image, the 28 by 28 image, which is not an image is nothing more than a two-dimensional array. So got this little helper function, and now you can build the CNN. Remember, we had this nn.sequential, which we developed in previous notebooks, and basically it builds a neural network layer by layer. So it starts with a convolutional layer with padding 2 and stride 2, followed by a ReLU. The next is a convolutional layer with filter size 3 by 3. That's what this 3 is. And the 5 is a 5 by 5 filter. The padding in this case is 1. The stride is 2. Remember what padding and stride are. Padding is the spacing around the edges of the two-dimensional array that are added. So if you have like just as an example, if you have a 10 by 10 matrix and you pad it with 2, that means you add an extra border line of 2 pixels all around it. Okay, and padding equals 1 means you add it, and that border line has zeros in it, or whatever you want. I think it's defaulted to zeros. So it's a way of it helps you when you apply the convolution. It helps you when you apply the convolution filter. So if the padding is 1, then it's adding a border of 1 pixel all around, kind of all around the array, right? And stride means what? It means when you apply the convolution filter, the 3 by 3 filter, every time you advance instead of by 1 pixel, you advance by stride, the number of pixels to advance. So if the stride is 2, you take that 3 by 3 convolution filter and move it to the right by 2 pixels the next time when you apply it. And remember, you sort of scan through the whole image with this, if you remember the convolutional network thing. So padding and stride are 2 parameters that are needed to define how you're going to apply the convolution. And then, so in each case, you apply the convolution, and then you apply the ReLU. And then, then there's a second layer where you do the same thing, except now you're doing a 3 by 3 convolution. And remember, this 3 by 3 has weights. It's 3 by 3 matrix of weights that have to be solved for, that have to be determined by our stochastic gradient descent. So these are parameters. And then another 3 by 3 convolution, this time with padding 1 and stride 2, followed by a ReLU. Another one, this time padding 1, it's again 3 by 3, followed by ReLU. So these are the layers. So there's 4 convolutional layers. Then there's an adaptive branch pool. And I haven't looked this up, but what it does is it takes in a matrix and does some kind of averaging. And that can be, I think if you look it up in PyTorch, you'll find out exactly what it does do. And then after all that's done, then you flatten it. Okay, because to apply the convolution, first you have to get it from a vector into a matrix. That's what this lambda function does here. And then when you're finished, you want to put it back into a matrix, into a vector. So that's what this lambda flatten does. And then the final is this fully connected neural network that you apply to this vector to give you your output. To give you your output, which is a digit, right? So that's what this CNN model looks like. And so this is the function that builds the model. Now we instantiate the model. Now the model is the real object. And then, so now he's going to use callbacks. And so from the previous notebook, 0505B, we had the recorder, which helps us to keep track of the learning rate while we're training. And then the partial average stats function, which is using the accuracy metric. These are things that we want to monitor our training. So we start building our list of callback functions. Remember, callbacks functions are a list, right? And so here's 2 elements in the list. Okay. The other blocks are building blocks that you need to actually run the model are the optimizer And so he's got this thing called opt, and we're using the PyTorch.sgd stochastic gradient descent method with the model parameters as the input. Remember, the model parameters are all the weights from the layers in the model, and he sets the learning rate LR equals 0.4, and then he builds a learner object, which, remember, the learner object takes as input the model, the optimizer, the loss function, and the data. So we've defined all of those things up to this point, and so we can build that. And so we've got this learner object, and then we build this runner object. The runner object takes as an input the callback functions. Remember, the runner allows you to run the model with whatever callback functions you specify. And we've got this list, CBFS is our list. So let's just get all that done. And to look at this runner, and this tells you, if you do this, it'll just tell you where it comes from. So remember that X is a folder that includes all of these transformed notebooks. Because remember, every time you finish the notebook, at the bottom, he exports the notebook, and it goes into a file in this little exports exp subdirectory. If I could, let me try something for a sec. I'm going to move to another notebook, to another tab in my browser, and I want to see if you can see it. So I'm going to move to this tab. Can everybody still see everybody see that I've changed the view?
Yeah.
Okay. So now I'm looking in the directory DL2. You know, remember the NB's directory and then it has subdirectories DL1 and DL2. DL2 is for this class, for this course, and there's a subdirectory in the DL2 folder. And remember, we're working out of this one here, the 06 CUDA CNN hooks. This is the one we're working out of. But I just want to take a look at this little X subfolder. I go into it. You can see all of the notebooks converted to Python code. That's what their method of development is doing. They're using this in the development of Fast.ai version 2, where you develop everything in a Python notebook, in a Jupyter notebook, and then you convert it to a Python file. And remember, that's what happens at the end of every notebook. He does the export thing. I'll go back up to our notebook here. And here's all of the notebooks that were built. And you can see that last night I ran through all of our notebooks up to this one and rebuilt everything. All the way up to notebook 7. And then these, starting from a 07A, that's what I hope to start with next week. Anyway, so going back up a level.
So basically, one quick question. So basically, whatever is in a hash export get exported into these notebooks.
Yes, that's right.
And this is going to be like a final Fast.ai library or API.
Yeah, for our course, yeah. And the rest of Fast.ai is built the same way.
So let's see.
Yeah.
Yeah.
So
what I was trying.
Yeah, go ahead.
Sorry. So what I was trying to get into is, like, let's say when we do, like in our project, we say import fastai.star. These are the py files. These are the APIs which get imported, or these are the functions which are available for us.
No, I think that you have to do this explicitly for the class. The files that we're building for the class, you have to import them explicitly, and that's why he does that at the top of every notebook. You notice he imports the previous notebook, the .py file from the previous notebook. Let's just take a look. I haven't done this before, but let's take a look inside one of these things.
Yeah.
So you see, it's auto-generated. This is the notebook.py file that actually was built after we ran this notebook, the notebook that we're working on. We haven't actually, when we finish this, the last thing we're going to do is rebuild this thing. So here's what it looks like. It's basically a Python file that can be executed directly from Python. Okay, it's basically a notebook translated into a Python file. So you don't want to edit this. It says if you want to edit it, edit the notebook, which is what we're doing. Okay.
Okay.
Yeah.
So in a sense, So in a sense, these nb.star files, they are just used in the different notebooks. It has nothing to do with the Fast.ai API itself.
That's right. This is just the infrastructure that we're building for this course. And so in order to have it available for ourselves, we have to import it. We have to, remember the first line in this notebook is, it says like you said, it's the import star. It brings in the previous notebook, which contained everything up to that point, right?
Okay.
And then at the very end of the notebook, when we finish it, which I hope we'll do today, you export the notebook. And starting with this notebook, they're implementing this new way of exporting that was built by Stas Beckman. And it's called auto export. And what it does is whatever notebook you're in, it just automatically builds it into this .py file and sticks it in the exp directory.
Yeah.
Yeah. Okay. So let's go back up to
okay. Thanks.
Yeah. And thank you for asking the question. It really helps me. I mean, I used to be a teacher, and it really helps me when people are interactive and asking questions and stuff. Because otherwise, I feel like I don't see your faces, I don't hear your voices, and I just feel like I'm talking to the wall. So it helps me when people ask questions. So feel free.
We're here, Joseph.
Yeah. Yeah. Thank you.
Thanks for the encouragement, and I'm going to keep you bothering now.
Yeah. Okay. I've created a monster. Okay. All right. So here's our, let's see, where were we? We were, okay. Okay, here we were. The get CNN model. I believe we had done this part, but and I had executed this one. So, and we started building our callbacks file. We built our runner. We looked at our runner just for a moment to see where it comes from. Remember, the runner was defined in previous notebooks. Okay, and now we're just going to run it. We're going to run our model and see what happens. So, and because we haven't done anything yet, we haven't specified anything else, it's just going to, by default, run on the CPU. And so it's pretty quick. It runs at about 10 seconds. So it's running. Can somebody mute? Let's see, there's some background noise. You can mute yourself unless you're going to say something, please. Thank you. All right, so it finished in 11 seconds, which Jeremy says is a long time. So it's time to use a GPU. We want to put the model and data on the same GPU device, and we can make this happen with a callback. So that's what's happening next. He's going to write this callback that puts everything on the GPU, and he has two ways to do it. So method one, you define a device using a PyTorch function. You define the device to be the GPU that you have. Of course, this isn't going to work if you don't have a GPU available. It's just going to crash. And then he defines this callback class, which puts everything on the GPU. And that's explicitly done here. You have a device, and then you have this model.to function, which we could look up. But basically, it puts the model on some device that you specify. And you not only have to put the model on that device, on the GPU, you also have to put the batch on the GPU, the batch and its labels. So that's what this command does. It puts the batch, which is XB, and the labels, which is YB, and puts that on the GPU. Okay, but actually what he uses is, what he's using for posterity is the second method. And he said it's somewhat less flexible. I'm not sure why, but we'll find out later maybe. So you just use this torch.cuda.setDevice device. And that's all it takes. We've already defined this device. So now it basically tells CUDA, that we're going to use the GPU. And then putting the model on the GPU is nothing more than .cuda, the model.cuda. And putting the batch is just batch.cuda, and the labels.cuda. It puts everything on the GPU. And now we want to add to our, remember we were building a list of callbacks that we want to have available to us. We're going to append this new callback, the CUDA callback. So that's what this next one is. So
quick question.
Yes.
Is there a way to specify constraints, such as the amount of memory available in the GPU card? because you may be training for a particular GPU, but you may or may not have enough space there?
That's a really good question, and I don't know the answer to it, but I think that is discussed in, I've seen something like that, I think, in the forums discussed. So you might go to the forums and ask that question. That's a good question.
Thank you.
Sorry, I don't know the answer. Okay, so the next thing is we're appending the callback. Let me just make sure I haven't done this already. I want to have a look at what does my CBFs look like. Remember, CBFs is a list of functions of callback functions. So let's see what's in it so far. It's more than a list. It's actually some kind of an object that contains a list. So I'll do that. I want to see what's in it and make sure that I'm not adding things twice. Yeah, well, here it is. It has average stats callback. It has accuracy, and it has CUDA callback. So if we did, oh, and it has the recorder. So it has it's already, I must have already run this. It's got all of the callbacks. 1, 2, 3, 4. These are the callbacks in our list. All right, so now we build a model again. And this time, we're going to, oh, and then we build the runner to run that model. And the runner takes as input the callback functions, which now has this extra one, the CUDA callback in it. And now we run it on the GPU, timing it. And I've already gotten to the punchline here. It's much faster. So, well, 4 seconds. I had 3.6 last time. But anyway, it was almost, well, last time it was 10 times faster. Maybe now it's not quite 10 times faster, but it's still almost 10 times faster.
How many seconds it took on a CPU?
Yeah, let's go back up here. The CPU, it took, I think, 11.4 for 1 epoch, right? So that's like one second per epoch, right? But on the GPU, we ran 3 epochs. So in 4.1, so that's like 1.5 seconds per epoch. So sorry, 4.4 seconds for 3 epochs is 1.5 seconds per epoch. And this was, sorry, I made a mistake here. It's 1 epoch in 10 seconds, 11 seconds per epoch. And here it's 1.5 seconds per epoch.
1.5, yeah.
Yes, yeah. So it's, it's almost 10 times faster. It's like 8 times faster, something like that.
Correct, yeah.
Yeah, it's a lot faster, let's put it that way. All right, so of course, Jeremy, being Jeremy, is going to make things better immediately. So he defines the sequential model. He defines a more general sequential model, which can take as an input the padding and the stride. And then, so now he's going to build this little cool thing where you can just iterate through this function and build all the model, unbuild all of your layers. So batch. Oh, but first he builds a batch transform, which you do the resize. Built a callback to do the resizing.
So what he's trying to do is like he introduced this padding.
Yes. Remember whenever you specify a layer in this nn.module, you have to specify the dimensions. KS is the kernel size for the convolutional layer for the convolution, which is, remember, either 5 for the first convolution or 3 for the subsequent ones. And then you have to have padding. And he says that an algorithm to decide the padding is just divide the, if it's 3 by 3, divide by 2, and this double slash means take the greatest integer. So 3 double slash 2 is 1, so the padding is 1. But if it's 5, for the first layer, the padding is 5 double slash 2, which is 2. So this is kind of like an automatic way to generate these parameters, and the ReLU. So this builds the layers one by one. This is basically a little function to build one layer. That's what he's doing here.
Yeah.
Okay. Then he builds a callback that does a transform. I'm not sure what this order parameter is, but it must mean that it's being done later on. It's being done in the second layer of callbacks or whatever. And here it's just begin batch. It's just going to have a begin batch on this. You're going to run the batch. run.xb is going to be defined as transform of xb, where transform is the input function that you're going to pass in. So you're going to, when you call this batch transform callback, batch transform x callback, you're going to pass in some transform that you want done on the data, and it's going to do that transform in the begin batch part. Okay? So that's a callback. And then view TFM is basically a function that lets you reorganize your data in some way that you specify. Where size, again, the star is, if you specify that you want the size to be 28 by 28, then star size means, yeah, you want the dimensions to be 28 by 28. Don't just use the first one, use both of them. Right? If you put in, so if the input is a tuple or a list, the star means go through all the elements in that list. Okay, so it's a way to, this is a little helper function that helps you to, that you can pass into another function that specifies how you want this tensor to be viewed. So if it's a vector, you can view it as a matrix, or if it's a matrix, you can view it as a vector. I think that's what this function does. So now we add this new callback to our list of callback functions. And remember, the callback functions can be they're all functions, because we've taken this class and we've made it into a partial. Why is this? Okay, we've made this batch transform callback. We've built it into a partial function, which means give it this input MNIST view. That's the input function. Remember, batch transform callback is a callback, but it takes as an input some transform function. And the transform function is this MNIST view that we're passing in. So that's what this does. And we're going to, so MNIST view in our case is going to be this view function with the input 1, 28, 28. And then we're going to add this to our list of callbacks, so that now when we look at our callback functions, CBFs, we look at our callback functions, and there should be 5 things in there now. We have the recorder, we have the average stats callback with accuracy, we have the CUDA callback, and we have the batch transform callback, and the view. Let's see, why do we have the view partial view? Let's see. Yes, functools partial. This whole thing is one. This is one function. So there's 5 things in the list of callbacks, just as we expect now. I just was curious about what this little cryptic thing is here, so I just did an experiment here to see. I defined size to be 1, 28, 28, and then I did this -1 plus size, and all it does is it adds on. The size is a tuple, and it just adds -1 to the beginning of the tuple. That's what this little construct does here, which we see here. So now he defines this NFs. Forget, this is, I wish I knew what this NFs is. If I were refactoring this, I would make this a word that you can understand. Right now, I don't understand what NFS is. I think it has to do with the dimension.
Bad software engineering practice.
That's right. That's right. That's what I think. But they
is that
like
the number of filters?
Yeah, I think that's right, Christine. NFs. So this tells you the number of filters for each layer or some. Yes, I think that's what it is. There's your layers. Okay, so again, I saw this line in here, NFS equals 1 plus NFs, and I know what it does. It basically prepends a 1 onto this list, but just to convince myself, I did this, NFs, and then I did this, and indeed it does that. It just it prepends a 1 onto the beginning of the list. All right, so now he's got this function that automatically builds all of your, that basically does the same thing as before. It builds your convolutional layers. It's these 2 functions combined. get CNN layers, and then get CNN model. So first, you generate all your layers with the first function, and then you call that, you generate your sequential model by just spooling out this get CNN layers output. That's what the star does. It says, include all of the elements. I think a star basically iterates through, if you have an iterable, which is like a list or a tuple or something that has elements that you can iterate through. The star just says iterate through all those elements and give me all of them. So that's the question that I think Dinesh asked before, and we see it. You got to get used to this because they use it everywhere and they also use the star. We actually explained that in one of the previous notebooks. There's these two constructs that they use all throughout the Fast.ai library. It's the star and an input. And an input list, you can use a star or a star. And the star means the same thing, but you have a list of, it's like a dictionary. So the star means go through all the elements of the dictionary. The star means go through all the elements of the iterable, what do they call it? The non-keyword inputs. And the keyword input is the dictionary. So the non-keyword input is handled by the star, and the dictionary input is handled by this double star. Okay. So here we go. We're going to build our model using this function. And yes.
Hi,
question?
Joseph. Can you just repeat the star and double star part? Like, I think I got confused there.
Okay. So when you have an input to a function, and if that input is a list that has to be iterated through, the star forces you to iterate through it and include all of the elements in it, right? That's what happened again back up here when we did the data loaders. We iterated through both elements of that list and made sure that include both the training data loader and the validation data loader down somewhere around here. I think.
Right there. It was go up, go a little bit up.
Oh, is that close? Yeah, there it is. There it is, the star get DLs. So remember, the get DLs function returns two data loaders. And but these data loaders are, there's these iterable objects. And I don't think I went through this carefully enough. They're iterable objects, and which means that you can call them again and again and again, and they'll cycle through all the batches, right? So the star in front of that says, get me all the batches. Okay, the data is not just one batch, it's all the batches. And so that's what that star means. It forces you to iterate through these data loaders. Remember, the data loader is like a black box that whenever you call it, it returns a batch, right? And the star forces it to iterate through all the batches so that you're getting the entire data set into it, right? Does that make sense? Okay.
Yeah, Joseph. And when we have two stars, then?
Yeah, and when you have two stars, it's when the input is a dictionary, is some kind of a dictionary, a keyword list. So it says to go through and iterate through all the elements of that dictionary. And the dictionary could be a dictionary of functions. It could be a dictionary of anything, you know. But the point is that the dictionary is a structure that has a keyword and a value. It has keywords and values in the dictionary. And the star means iterate through all the keywords and all the values. So that's what we don't
so
see.
in the first case, when we have a single star, it's just like we are going through maybe a list, right?
Yes.
But when we have two stars, we are going through a dictionary with
Yes, that's right.
Key and the value pair, right?
Yes, and that's right. And someone asked, what use is this? I think when we were describing this a couple of weeks ago, somebody asked, I think it was Jesse, Jess. I think Jess asked, what's the use of this? And here we see it. It's actually, it's not just going through a list. If the list is composed of iterables, it actually forces you to iterate through all of those. So that's what we see when we when we put a star in front of the data loaders, because a data loader is one of these, what do you call these things? It's an iterable, definitely, but well, remember, the data loader is a black box that every time you call it, it generates the next batch. It remembers where you were. So if you call it once, it'll generate the first batch. If you call it again, it'll generate the second batch, and so on. And it'll keep going until it gets to the end of the data. If you keep calling it, it'll keep giving you batches till it gets to the end of the data, and then it will stop. And so the star forces it to run through all the batches until you get to the end of the data set. So it's really a powerful concept. Okay, let's try to resume here. We're almost 15 minutes. We're not anywhere near done. But let's see. All right, so where are we? We just built the model. Yeah, I think this is the last thing I did. So yeah, then we did this, then we did this, then we ran that, and now we're ready to, okay, then he built this function again, export. This is going to be reused in the future. He built this function called getRunner. And the input is a model, the data, the learning rate, the callbacks, the optimization function, the loss function. Okay, in this case, the optimization function is a keyword argument and can be specified. The callbacks is a keyword argument and can be specified. And the loss function is a keyword argument, but it has been pre-specified. So these things are preset to none. So the function, this getRunner function, is flexible in that you can give it a list of callbacks and you can give it an optimization function. So, and then inside the function it says, if opt function is none, that is if you haven't specified one, then use a stochastic gradient descent from PyTorch. Okay, and so then it sets the optimization function. It sets the optimizer to be the optimization function given the model parameters and the learning rate. And so now we have opt, and then now we can build the learner object, because remember the learner takes 4 things as an input. It takes the model, the optimizer, the loss function, and the data. It's a really cool way to just combine all those into one structure. And then so it builds that thing, and then it returns both the learn object and the runner. And remember, the runner is, it basically takes as a list all of the callback functions that you supply it. Okay, it listifies them. And so that's this helper function. Let's compile it. Now we can build the model and the learn and the run object. And now we print the model just to look at it. And I just added this little line that tells you, that counts all the layers. So it tells you, so it's a sequential layer with a convolutional kernel 5x5, stride 2, padding 2. The second layer is a convolutional layer with a kernel size with a convolution of 3x3, another 3x3, but it expands it into 16x32. And then the final layer is 32x32, kernel size 3, stride 2. And all of these things were built by these helper functions that he put in place. Oh, and remember that each one of these sequential layers that has a convolution in it is followed by a ReLU. Then he does the adaptive average pooling, the lambda, which is, remember this, the lambda takes the two-dimensional array and flattens it out. And then you apply this linear, the final layer is the fully connected network, which has weight, which maps this into 10 output features. And it includes a bias. So remember, this is one of those linear transforms with the weights and the bias. So it counts the layers. We have 7 layers in the model. Next, we can run the model. And I put the little magic command %time in front of it just to time it again. 4 seconds to do 3 epochs. So that's like 1.33 seconds per epoch that we're getting from this, from the GPU. And the final accuracy is 0.95 after 3 epochs. Okay. All right. The next thing is hooks. Yes.
So what's the difference between this model and then one we just ran before. So is it that accuracy got increased?
No, it's exactly the same model. It's just built in a cooler way. Jeremy likes to make things cool. So he built this these little helper functions that built the model in a very nice more automatic way than before. It's less manual. Everything he does when he refactors things is to make it more automatic. And that's
okay. So it's just a refactoring.
That's right.
Okay.
Right. So
All right.
yeah. So he built the model with this getCNN model function. Then he built the learner and the runner. Remember, he used to have functions to build the learner, and he used to have another function to build the runner. Now he combined them into one, which is getRunner. It builds the learner and the runner. Okay. And remember, the learn object is the object that takes everything you need to. It takes everything you need to do training in it. It has the model, it has the optimizer, it has the loss function, and it has the data. Those are all the 4 things you need to be able to train the model. And the runner is the is basically a training loop with all the callbacks that you want. So the runner tells you how to do the training, and it has all the callbacks that you want to use. All right, so that's what we did here. We ran the model, and now we have this section called hooks. Now hooks are this. We have callbacks that we built our own callback system in Fast.ai, but hooks are something we inherit from Python from PyTorch. It already has these. Basically, they're callbacks that are built into PyTorch that allow you to do things inside of these sequential models. So that's what we're going to do next. So he has this sequential model. I think we've built a class like this before already. It's an NN module, and it has layers in it. And the layers are defined by this module list, and it collects the means and the standard deviations for all the layers. It has this call function that I looked up because I hadn't seen it before. The call function is different than init. Notice what it's doing. It's actually cycling through the layers. It's iterating through the layers and building step by step. It's building a sequential model because it applies each layer to the output of the previous layer, right? So I is going to be 7. There are going to be, sorry, I is going to range from 0 to 6 because remember there were 7 layers. So and each time it's going to start, it's going to get the layer, apply it on the input, and then replace the input with the output of that layer. And then when it comes to do the next one, it's going to apply the second layer on that input and then replace X with the output of that. And it's going to cycle through this until it's applied all 7 of the layers. So this is what I mean by automatic. He's basically building this thing automatically using this call function. And I looked this up on Stack Overflow, which is really helpful. I'm sure all of you know it. And I found this sentence that was useful. The init method happens when the class is called to initialize the instance. Remember that a class by itself is basically just a schematic diagram for building something. You haven't built anything yet when you specify the class. But then when you actually say, X equals sequential model, blah, 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 now you're actually building an instance of that model. That's what they mean by initializing the instance. When you call the class and build something with it, that's the instance of the class. And we already knew about the init method, that every time you instantiate the class, the init method happens and you get this initial, it initializes your layer, your methods and whatever you want it to initialize. But the call method happens when the instance is called. So after you've built the instance of the class, every time you use that instance or call it, then it goes through this call function, this call method, I should say. Okay. So I thought this might be helpful to you.
Yeah, and just to add, I heard one of the snippet where Jeremy said, once you have a call method within a class, you can call that class as a method directly. So if you see down here,
yes, that's right. That's right. That's right. You could call the class as a function, and I think that's important because he uses that later on. That once you have this call method, I forgot about that. Thanks for reminding me. Once you have defined a call method, now you can actually use the sequential model as a function. And that's what he's doing here. So he's using sequential model the same way you would use a function, by giving it inputs. And remember, this star does is it forces it to iterate through all the layers. That's what it does. Okay, so now he builds the model in this way, which is building the same model. Let me run that. Building the same model. And again, he builds the runner the same way. This time he changed the learning rate, I think. Where did he? He had a learning rate of 0.4 there. Now he has a learning rate of 0.9. Not sure why he did that. The callback functions are the same, I believe. Remember, this CBFS is what you've already defined. What we have already defined is our list of 5 callbacks. And the CBs is the keyword argument. Remember, this thing has a keyword argument. Get CNN layers has a keyword argument. Let me go back up here. Get CNN model. I saw this. I saw the CBs argument. Let me see. Find out, where does CBs occur? CBs. Is that the first place? CBs. I want to go up to the top and find the first instance of CBs. There it is. It's this get runner. Get runner takes as an input CBs, and it's not specified. That means that you have to specify it if you want to. And so if you don't specify any callbacks, you'll get the runner without the callbacks. That's fine. But if you want to use callbacks, then you have to supply it as a list, as a keyword argument that's CBs. So that's what we did here. We gave it the key. We passed it the keyword argument CBs. Sorry, I did something there. There, CBs, and we gave it this real list that we've already built, CBFs. Okay. So that was up there. Now we're in this hooks section, and I did this. I think I did this. So now we're going to run this, and it's the same thing, really. We haven't done anything yet, I believe. Let's see. Yeah, we're just building the model in a different way now. It's the same model. The only difference is we've got a higher learning rate. Let me make sure I did this. Run that. Run that. Should be pretty quick. We wanted 2 epochs. So in 2 epochs, we got up to 90%. I don't think that means that's not. It doesn't matter. If we change the learning rate, we get a different result. Okay, now we want to look at the evolution of the means and standard deviations of the activations during training. So we do that. We've actually recorded the means in this sequential model. That's what's interesting here. We are actually now reaching into the layers and getting some interesting output, which is the means and the standard deviations of all the layers. And so this is what it's doing here. It's going to plot those for us. 0 to 5. Why is it 0 range of 6? I thought we have, oh yeah, there are 7 layers that are interesting for us, and those are the, sorry, there are 6 of the 7 layers that are interesting for us, and those are the ones that before the final layer, because they're the ones that have the convolutional layers. So we're looking at the weights. We're looking at the means and standard deviation of the weights, and notice how they start near, this is the first plot is the means, starts near 0, we knew that, but as you run through training, and you execute all the batches and so on, you see that it wildly fluctuates. And then eventually it runs away from 0. And now it's all the way up to, like, some of the layers have weights. In fact, the deeper the layer is, almost, some of the deeper layers have really high means. They're going up to 0.6, which is sort of something you didn't want. You wanted the mean and standard deviation to be 0 and 1. Yeah. Yeah,
so the pink line. So yeah. Which layer is this pink? Which
that's a good question. I see this purple here. I think that's what it is. This one is, so it's layer 4. It's layer 4.
Interestingly, the mean is going away from a 0 for all the layers. It's only the pink
Except
which
for that-
stays around
That's
0.
right. Yeah, so that's interesting. Let's look at what this pink layer is. It's the fifth layer. So back to our model description. The 0th, the 1st, the 2nd, the 3rd, the 4th, and the 5th. So the 5th is just, why do we even want the 5th layer? The 5th one is after the adaptive pooling. And all we're doing is we're expanding out the array into a vector. So I believe, I got that right? 1, 2, 3, 4, 5. Oh, it's this one, adaptive average pooling. It makes sense that that one would be close to 0 because you're just taking, you're just taking some kind of mean. That's interesting. That's the one. But Dinesh pointed out that that's the one that stays close to 0.
Okay.
Yeah. But its standard deviation is not well behaved because look, the pink one is the worst. So what happens? So the second plot is the standard deviations, and remember, the standard deviations. Wait a minute. We're plotting standard deviation. Why standard deviation is close to 0? We want the standard deviations to be close to 1.
1, yeah.
Yeah. So it gets to, after a while they get close to 1, but then they take off. At least some of them do, and get way bigger. So that's not optimal. So we got to do something in our future work. We're going to do something to fix that, I guess. So make sure I ran that. These things are different every time you run them too. So.
And if I'm not mistaken, we are alluding towards the initialization that we haven't done any.
That's right. That's going to be taken care of in the next notebook, the batch norm, which I think we're going to have to defer till next time. And we're late already, so I'm sorry. But you guys can run through the rest of it. It's just some of these plots. And there's something about a hook class. Then I'm sorry, we didn't get to the end of it. But we've basically done most of it. The hooks class is letting us peer inside of these sequential layers and get the statistics out and plot them in histograms. It's a really useful thing.
Yeah. So can we maybe next time we start from this hooks and quickly?
Yeah. I have to apologize to everyone. We're not getting through we set ourselves a pace, and we're not getting through in the pace. But I think it's way better to actually understand things than to rush through them.
Totally agree. Joseph, don't worry about, I think, more than happy if we go into detail and then we all are like on the same page. So
yeah, that's what I like.
I would rather have, as you said, go slow and then understand the concept rather than zip through not understanding.
Yeah, and I see that I'm over. I'm sorry I ran over, so I'm going to let you guys all go because some of you have to go to the, probably have already left for the next class. Yeah.
Joseph, it looks like there may not be another class today. I think Avinash is not hosting it.
Oh, okay. Well, if anybody wants to stick around, I'll be happy to go through this. And then for the ones that can't stick around, we can take up where we left off here next time.
So, don't you need to? I'm more than happy to stick around if there is no next class. But how do we check?
Go to the Slack channel. And look, they usually tell you, they usually warn you about this.
Okay.
There's usually some conversation about that. Yeah, so if you're worried about missing that class, go ahead and check it out on Slack. Otherwise, I'm going to stay here. I'm going to stay here and go through the rest of this notebook at least. And so anybody that wants to stay, I'm going to stay.
Okay, so I'm just reading it through. They haven't found any host if somebody wants to host.
Oh, so they're still waiting. Okay. So if somebody hosts, if you'll keep an eye on that, Dinesh, and
I will.
Let me know if and when they start, and then I can stop what I'm doing so people can go.
Okay, and I'll post the message as well over there.
All right, thank you. I'm gonna right now, before I go through the rest of this, I haven't had a chance to look at the group chat, see if there's anything I can answer. Yuri. Yuri is on our chat. Interesting. Okay. Interesting. Yuri is the guy who runs the MLcourse.ai.
No. I'm a different Yuri.
Oh, I'm sorry. I'm sorry. Okay. Hello, Yuri. All right. So what do we have here? I'm just running through the comments real quick to see if I can address any of them. So Yuri, you were answering questions about people were asking how to register for that class.
Yeah, I registered myself, but I haven't been able to get on the Slack yet. So I'm assuming that's where they're going to post all the information.
Yeah, let me see. You filled out that form that he asked for, right?
Yeah.
You should have gotten an email from them that signs you up for the Slack. So you should be in that. You should have gotten an email about that. Look in your emails and make sure you didn't get one.
Yeah, they also said try registering with another email. I might do that.
Okay. Yeah. Good. Okay. Yeah. So there are links to all the lectures on YouTube, and so before you get into Slack, you can still have access to the lectures and stuff. I'm not sure about the assignments, but I think they might be publicly available as well. Yeah, somebody asked about the notebook. Yeah, I'm just running through the 06 CUDA CNN hooks init notebook and it's basically the original notebook for today. Somebody's microphone isn't working. Participants class are really top notch. Yeah, but don't be, the participants in MLcourse.ai are really top notch. Well, yeah, don't let that scare you off. I'm sure it'll be fine. There's many different levels, and I'm sure that anybody can get something out of this class. If you have the experience to get something out of the Fast.ai classes, you're certainly sophisticated enough to get something out of the MLcourse.ai. But that being said, there are a lot of really good people in there. These Russians are really take their machine learning seriously. They have the math background, a lot of them too. They have the Russian school system, I think, is a lot better than ours, and the people that come out of there are mathematically way more sophisticated than Americans in the same. Like, if you graduate from school with an engineering degree in Russia, or a math degree, or a physics degree, it's likely that you're way more sophisticated than an equivalent four-year graduate in the U.S. I don't know if that used to be true, and I don't know if it's still true, but anyone who's from Russia can correct me if I'm wrong.
I'm not from Russia, but I agree with you, Joseph.
They take math very seriously.
Joseph, just an update. I don't think I haven't seen anybody in NLP willing to host or nobody came forward. I post the message here, there. So we just continue here. I'll update you if somebody says we want to host, but just I think it's 10 minutes already. So we continue here.
Okay, we'll do that. All right. So somebody asked what notebooks we're working from. Well, I have a GitHub repo which I try to keep updated. The GitHub repo includes all of the original Fast.ai notebooks and the ones that I've modified. And you should see on Slack. Did everybody see the notice come out on Slack? I think I had it coming out at 6 o'clock this morning for this meetup. I didn't check Slack today, but it should have come out. Let me look. Slack. On the Fast.ai DL, yeah. It was posted at 5:13 a.m., which is good. If you look on Slack in the Fast.ai _DL channel, there is the notification for this meeting that I have automatically generated every Saturday morning at 5 a.m. And
Joseph, are you showing any, and are you sharing any screen?
Yeah, that's a good point. I will share that. I'll stop.
Okay, so we don't see.
Yeah, I will share. Sorry.
Okay.
I will now share that. Good idea. Okay, there it is. Okay, everyone, are you now seeing it?
Yep.
Okay, so this is the Slack channel, the Fast.ai.fastAIDL channel. Hopefully everyone is in this Slack group, the TWiML AI Slack group. If you're not and you want to be, there's this link here to sign up for it at the bottom. Okay, this is a site run by Sam Charrington, TWiML and AI. He has a podcast called TWiML and AI, and he has graciously allowed us to use his Slack channel, his Slack operation for our class, and that's what we're doing here. And so if you want to sign up to get the announcements by email, to get the announcements for these meetings by email, you sign up here, and you can join this group. You can join this TWiML AI Slack group if you're not already in it.
Joseph, can you click on General real quick?
General, where's General?
On the left side. There's a left, no more left.
Oh, left. Oh, yeah.
The channel here.
Yes, that channel. Let's see what that is.
And scroll down. That's me. I just wanted to do a little advertisement here. I also have a podcast, so if you're into that type of stuff, you can listen to the latest episode on theory of distributed computing, where I talked with Philip Schneider. So yeah, that was just my advertisement.
Excellent. Well, yeah, these are the things you could bring up at the beginning of the meeting when we ask for, this is the kind of thing. Yeah, but this is great. So you posted that on General. Okay, back to where we were. So this is the meeting notification that comes out every Saturday. And in that, you have a link to join the meetup. This is the Zoom meetup. You can just click on that and you're in the meeting. If you want to join by phone, you could do this. And then this gives you our current schedule, which I'm going to have to modify. So are you seeing the schedule? Are you still seeing the Slack page? I'm going to go to the schedule now.
Just Slack here.
Yeah, I'm going to go to the schedule.
Joseph, could you please post the link to the Slack channel onto the chat in this Zoom?
Absolutely. Okay, I'll do that. Okay.
And perhaps I think this is if we can pin it.
Pin that post. Okay. Okay. You want me to pin the link to the Slack channel?
Yeah, this schedule, I think.
Yeah. So now we're looking at the schedule, right?
Yep.
Okay. So that was this link. I have a link to the schedule. I'm going to have to modify this because we're getting more and more, it's taking us more and more lectures. But that's okay by me. I don't know if anybody's in a hurry. I'm not. I want to make sure to get through the class and take everybody with me. I don't want to leave anybody behind.
Yeah.
So
I think because I think the rest of the lessons are on a Swift. So I'm not if you ask me, I'm not very keen on a Swift for TensorFlow lessons. So I would rather spend more time on these Python lessons,
Yeah, I think the last two, 13 and 14, are Swift. But, I'm going to try to get through those as well. So we're just going to take as long as it takes. And if you get bored and want to stop after the Fast.ai part, that's fine.
Okay.
Anyway, so here's the link to the schedule, and I'll be editing it probably, we're already a week past the November 16th, but anyway. And then I'll go back to the Slack channel, here. Now we're back on the Slack channel. And the other thing that I put in here is the GitHub repo. So if I click on that, this is my GitHub repo that I made specially for this class. So I'm going to click on that and go to it. I'm going to share it now. Deep learning, screen one. This should be it. Share that. Okay, does everybody see the GitHub repo?
Yep, we can see it.
Okay, so here it is. And you see what's in it. It has the original notebooks, which I try to refresh every once in a while in case they've, I pull them directly from the repo, from the Fast.ai repo. So the original notebooks have the original names, and then the ones that I've modified have _JCAT on the back of them as a suffix. And these are the ones that I've annotated, put comments in, explanations, maybe some cases some new material, and so yeah, so you can look at these and hopefully they will help you to make your way through these notebooks. as you see, I'm just going along. I haven't gotten, just today I'm starting the 06, my own comments on that one. And the 07, I've already copied it, but I haven't done anything to it. This is just a copy of the original 07, which I plan to annotate. So that's how I'm making it through. Every week I'm annotating some of these, and by the end of the class, I'll have annotated all of them. Okay, and hopefully made them clearer for people to understand.
And you are going to post the link of your repository to the Slack channel as well.
Yeah, let me do that right now. I'll just copy the link.
Thank you.
Post it to the Slack channel right here. So this is the.
Hello, Joseph.
Yes. Hello. Hello.
Hi. You can hear me now. My microphone was not working. It's right now. I kind of got to make it work.
Yeah, I can hear you. Yes.
Yes, yeah. So I saw the repo just now, the Fast.ai deep learning repo. I kind of got it, and I saw the notebook, and it looks good. I just wanted to just confirm that. Just get my microphone to work. It's just working now. Feels good to interact.
Okay, great. Thank you. Okay, so I'm posting the link to the GitHub repo. Let's see, there's a way to make this. Oh, no, there's not. I'm not impressed with Slack because you can't make things pretty. At least I don't know how. Anyway, so the GitHub repo is for this meetup for the AI. This is a long name. TWiML study group is at. And here it is. I'm going to post it right now, and we can make this a thread if anybody started. I'll start a thread, and I'll also, can I pin it as well?
I mean, Joseph, another way would be for people to follow you on GitHub at jcatanza, and then they can also find the repo.
Okay. Yeah. Could you put that note to? Could you put a note to that effect in there? On this thread, I'm going to start a thread, and I'm also going to. I'm not seeing how to pin it.
So there are, if you just hover over on your post, and then click on like a more action, 3 dots.
More action, okay.
And there is a pin to channel.
Oh, more message. I don't see. Oh, there it is. Yes, pin to channel. Okay. Okay. Done. Thank you. Thank you. So it's done. Now, so you can follow me on GitHub, and you will be able, or you can just use this link directly. But that has all the notebooks. That has all the notebooks that we're working from. And I think somebody made this suggestion to me early in our study group. He said, "Why don't you put everything on? Why don't you put things on GitHub?" And I forget who made that suggestion, so I followed up on that suggestion, and I'm grateful for it. Okay, I'm going to go back to the actual notebook that we're working from. And so. Okay, hold on for a second. I'm getting. I lost my notebook, but I will find it in a moment. So I know where it is. Here we go. Okay, back to sharing the notebook. Can everybody see that? We're in notebook 6.
Yes, I can see it.
Okay. Now we just went through right before the hooks class, and we saw that the means are unstable. Oh, we didn't get to that far yet. Okay, the next 2 plots are zooming in to the start of the training session. It's basically the same as these plots, except we're zooming in on the first 10 or so elements. So it's basically zooming in on this part, maybe before the spike. So we see that at the start of training, the means are relatively close to 0. The biggest one is 0.15, and the lowest one is minus 0.25. And the standard deviations are actually not where we want them. They should be close to 1, remember, but they're not. So this isn't good. And this is what we're going to correct when we do the next notebook batch norm. But meanwhile, we're going to learn something more about the PyTorch hooks, which is their own way of doing callbacks. Hooks are PyTorch object that you can add to any nm.module. So basically, the hooks are a way of reaching into the module and seeing what's going on inside the module. And what's going on, we want to look at the weights and the biases and the parameters that we're solving for. So that's what's cool about these hooks, is that you can actually start to see what's happening inside your model. I really love this concept. So they work by registration. It gets, a hook will be called when a layer that it is registered to. So you register a hook to a layer. Remember, the layers are these sequence of transforms, these sequence of convolutions and other kinds of transforms that we built. Remember, we had 7 layers in our model. So each layer, you can register a hook to it, or one or more hooks to it, and then you can actually get at the numbers. You can get at the weights and the biases and so on, which is really important while the model is training. So you can actually do these things during the forward pass or the backward pass by making a forward hook or a backward hook. And the cool thing about hooks is you don't have to rewrite the model. Your model is done, and the hooks basically is reach into it and pull out outputs that you're interested in. So this is a really powerful concept. Let's run this thing again. It's the same model really, but now we changed the learning rate. And we're initializing the ACT means. I'm not sure what ACT stands for, but basically these are the means and standard deviations of the model parameters. So let's run that, initialize. We check the length of our model. I just want to remember that it has 7 layers. Okay, and now it's attaching a hook. So a hook has to have a function that takes 3 arguments: which module, what's the input, and what's the output. So append stats, module, input, output, and I is I think I indexes which layer in the model we're at. Yeah. So it takes as an input the layer number, the module, the input, and the output. And so just define this append stats function. And then we're going to register a forward hook. We're going to register this append stats function as a forward hook, which is basically we're going to use this function as a callback inside we're going to insert this function as a callback inside of our model. And the model is already built. We're not doing anything more to the model. We don't have to change it. So let's do that. I think I've defined that function, and I register the stats callback to every layer in the model, because that's what this does. Enumerate model. That means go through all the 7 layers and register this forward hook. And then I just wanted to see what this means. You can read about it. This function, register forward hook, is a PyTorch function that registers, basically attaches this callback to this module. Okay, so that's what we've done. And now when we run this model, we're going to be able to get out of it all of the stats that we want. We run the model, just 1 epoch this time. We only got up to a 30% accuracy. And we can look at, now we have our statistics because they came out of our model. And you can see that the means are very unstable. They start at 0, but they can spike up as high as over 1. So remember, these are the means that were generated by our hooks that we defined. Okay, so now, of course, he's going to refactor this and make it nicer and define a hook class. It's going to have an init method, which is going to be a register, register the hook. It's going to have a remove method. For some reason, it's important to remove the hook after you finish using it. So he builds this remove method, this remove function that then gets built into this delete method. Okay, and then he defines the append stats, a means of accumulating all the statistics on your training, on all of your batches from the training. Okay, and he says that in Fast.ai we use a Boolean parameter to choose whether to make it a forward or backward hook, and in the above version we're only using forward hooks. And where's that Boolean that he's talking about? I don't think he's needed it yet. He'll use it later when he defines backward hooks. All right, so now he's gonna, remember this is export, this is for export. So we're gonna be using it and reusing it later. Now we build a model again. Again, the learning rate is 0.5 and the callbacks are the same callbacks we had from before, I think. I don't think he's added anything to them. Let's just check. I'm gonna insert a cell. I just want to check that the callback functions, the CBFs, remember that's the list of callback functions that we're going to use in Runner. I just want to check that that's what it was before. Yeah, it's got the recorder, it's got the average stats callback, it's got the CUDA callback, it's got the batch transform callback. Yeah, it's the same set of callbacks we had before. Fine. All right, so now we can build the learn object and the run object in the model. And now he's going to instantiate this hook class. And hooks is going to be a list. And you see what he's doing. He's using a list comprehension. He's going to hook L. L is a layer for L in children of model up to 4. So he's going to build these hooks for the first 5 layers. That's why he's going, oh, for the first 3 layers. See, that's what he's doing. He's using only up to layer 3. So it goes 0, 1, 2, and 3. Does everybody see that? That's what this :4 says. So he's using the first 3 layers and building hooks into them. Let's go look at what these first 3 layers are. We have it up here. So we have the first convolution, the second convolution, and the third 0, 1, 2, 3. These are all the convolutional layers. So he's building hooks into all the convolutional layers. Layer 0, 1, 2, and 3. That's what this thing's doing. Does everybody see that? Where are we back? We are here. So he's running model from up to 4. That means 0, 1, 2, and 3. This is a Pythonic thing, right? It's just taking the first 0, 1, 2, and 3 layers in the model.
No, but I think when you say :4, isn't it like from 0 to 4, 5 layers?
No, the colon tells you you stop before you get to the 4. Right?
I thought the limits are inclusive.
Okay, let's show you. So I'm going to build this little vector. Okay, and now I'm going to go A from 0 to 4. And you see, it gives me the first 3 elements. It stops before you get to 4. That's the Python. 4. That's what's weird in Python. See, I'm used to MATLAB, and when you do this in MATLAB, it gives you everything up to including. Yeah. But in Python, this is the weird thing about Python. Yeah, right. So yeah. All right. So now we have these hooks. We've instantiated these hooks for the first 4 layers, that is all of the convolutional layers. That's what they're doing. So now we run the model, and then we can actually go into the model and extract all the information that we want using this hooks feature. So for agent hooks, that means the 4 different hooks that we built. We're going to plot the stats. H.stats of 0. And stats, remember, it gives you the means and the standard deviation. So stats of 0 is the means. So we're seeing the means right there. This is essentially the same thing we saw before, that it has all this spiky behavior. Whoops. Okay, now why is it behaving better? Well, I wouldn't say that's better. Anyway, it doesn't have spiky. Oh, the spiky behavior was from zooming in. Was it? No? This is weird. I was expecting similar behavior to that because we're doing the same thing, but we get something different. That's okay. Oh, I know why. Because we've advanced the model. Remember, yeah, the model is not doing very well right now, as you can see. The accuracy is 0.3 on the training set and 0.7 on the validation set, which is very strange because we've only run 1 epoch. So anyway, I think that's why things look so weird. Okay, now he's going to, as Jeremy does, going to improve things. He's building a list container, and it has get item, length, iter, set item, delete item, and represent. These are all of the methods. It's basically a container for a bunch of methods that he wants to apply. And the repr method just gives you a name. If the length is bigger than 10, the result is the result plus blah, blah, blah. I'm not sure what that all does, but we'll see it in action. And he's exporting it, so he's built this for, he's built it to last. He wants it to use it. He wants to reuse this code. So let's see what this does. List container, and we pass it in. Oh, and it has no, it's inheriting from nothing. It's its own class. He passes in, oh, and when it does init, it's going to take a list of items. So the items get passed in. Items are something that gets passed in. In this case, it's this range object, and he's going to listify it. And so the range goes from, again, 0 to 9, because range of 10 gives you 0 to 9. And that's what you see. There's the list container. And if you give it range 100, it will have 100 items. So now he goes T equals list container range 10. And then he's just showing how to get at the list container. So T is the list container. You can access it using a list of indices, or you can access it by using a mask. And this is the way, so he's got 10 items. The first, he's accessing it by a mask. False, 8 instances of false, and then a true and a false. This pulls out the 8th element, as you can see. And this pulls out the first and second element. So he's demonstrating how you can use this list container thing. Okay, so now he uses list container. Okay, list container, remember, is a class. And now he wants to build a hooks class that inherits from list container. So it has this init method that you go to super init, which means that you're using the list container method of init, which is here, listify the items. So he's inheriting from the parent class, and then he defines this enter method and this exit method. I must admit I haven't looked these up yet. These can be looked up on the Python reference site. Let me just divert a small divergence to get there for a sec. I'm going to pull that site up, and I'm going to share it. Share this. So this is can everybody see the new screen? I've gotten the Python 3.7.4 documentation.
Yeah.
Basically, it's just docs.python.org/3 for Python 3. Now here you can look up anything you need to know about Python, and you can do a quick search. If we want to understand what this delete method is, what is this, and what is this enter method? The dunder method called enter, which I haven't seen before. So go and searching, and there's all these references. And I think the best place to look for it is in the data model. So data model. I'll use Firefox finding page to find dunder enter. Okay, so here it is. Object dunder enter. Can everybody see that? Hello? Can everybody see the page we're on now?
Yeah.
Okay, and we've looked up the dunder enter method in the Python documentation. And it says enter the runtime context related to this object. The with statement will bind this method's return value to the target specified in the as clause. That doesn't help me much. There's other ways to look this up. Probably on Stack Overflow, you can ask what is dunder enter in Python. So these things are, remember in a couple of notebooks back, Jeremy gave a list of these dunder methods that we should get familiar with. And included in that list was dunder enter and dunder exit and dunder del. I forget which notebook that was, but so we definitely want to become familiar with these methods because he's using them. So back to the notebook. Okay, I'm back to the notebook now, right? And we're looking at this this hooks class that he built, and it has this.
One
yes.
quick question. You see in a dunder init method of a hooks,
yes.
and it's calling a super, and
yes.
method of a super, he's passing that hook again.
Yes. So the super.init means use the parent, use the initialization method from the parent, which is a list container class. So here's the list container init method, and the init method says self.items equals listify of items. So he's passing in the hooks for m in m's, m's f, super init of hook of mf. Remember, m is an index for the layer, and he's got this list comprehension. He's passing in all of this. He's passing in this list that he generates on the fly. Hook, this generates a list. Let me see if I can do this.
Where is the function hook?
Hook is a class. Hook is a class somewhere.
That's another class.
I believe.
Because this class is a hooks class.
That's right. That's a good point. Let me look up hook on this page and see if we can find where it first. I want a match case, and I want to find the next.
Okay,
yes.
that's another class.
So there is a class. Yeah, there is a class called hook, which we already went over, but I've forgotten it already. So yeah, so see what it is. It registers these hooks to each of the layers that you give it. So that's what this is doing. It's building. So if I go back to the next, let's find the next instance. Oh. In the hook. Yeah. So what if I did this? Yeah, but I need F. I need M and F. This is, you understand what this is? This is a list comprehension.
Yeah. Okay.
It's generating a list of these hook classes. So it's a whole list of hook classes that are specialized for each layer, for each of the layers. So it's doing that. Okay, and then it has this del item method and a remove method. For some reason, it's important to remove the hooks after you've used them. And so that's why he's building in these methods. So let's run this. Let's see what happens now when we run the model. remember, we haven't changed the model at all. Here he has an fs.CUDA. I guess this is another way to make sure that it gets run on the GPU. Is this the way we've been doing it? I didn't notice this. He's running the model slightly differently. I guess he's running the model directly here. Model, learn. Okay, do this. We build, I think we did this. Hooks equals hooks model append stats. Model append stats. Okay, so I guess this is building all the hooks we need to get into all the layers that we're interested in. And it returns 7 items. Object. It doesn't give you a very definitive, a very interesting or interpretable list of items there, but these are the 7 hooks that we generated. Then he says hooks.remove. So we've got this list of, this is a list. Small h hooks is a list. And now he's going to remove them. And I'm not sure what's going on there. Now he's generating the next batch from the training data loader. This is how you use the training. Remember the data loader that we talked about? Data.trainDL. Data is the data bunch, and .dl is the method that gives you the data loader. And to get at the data loader, to actually call the data loader and generate the next batch, you have to use next of iter of data loader. Okay, so that's what we're basically generating a batch here. And we can, and then he's using the mnist resize function to make the batch into an array, to make the batch into instead of a 728 length vector, it becomes a 28 by 28 array, and then he puts it on CUDA. He puts it on the GPU. We executed that. Now let's look at what we got. Oh, you know what? Before we do that, let's execute it again. And I want to do x.shape. Let's have a look at it. And now we do this, and then we can print. I don't know if this is going to work because we'll see. Shape might not work on a one-dimensional vector, but let's see what happens. Oh, it isn't going to be a one-dimensional vector. What do we expect here? We expect a batch. We expect a 2 by 2. We expect a 2 by 2 array. I'm sorry. And we expect a 2-dimensional array, and it's going to have the number of rows equal to the number of items in the batch, and each row is going to be 700. It's going to be a vector of 728 elements. So that's what I expect here. And what I expect here is instead of a batch of 728 length vectors, I'm going to have a batch of 28 by 28 arrays. So let's see if what we expected actually happened. Yeah, so here's what we expected. 512 elements in the batch, because 512, remember, that's the batch size, and 784. Each element in the batch is a 784 length vector that represents the image of the digit of the mnist in the mnist database, right? And now we have the second print statement is after we did the mnist resize. And remember the mnist resize function basically resizes it into it takes the 784 length vector and puts it back into the array that comprises the image of the digit, right? So what we expected to happen is what happens here. So it makes sense. Okay, now we're going to look at this x.mean. And remember, this tensor is now on the GPU because that's what we did. We put it on the GPU with this statement here. So when we take the mean, it also reports that it's on the device, that it's on the GPU. And we see that this X has a mean of roughly 0 and a standard deviation of 0.98. And remember, the pre-processing that we did, that's what we normalized the entire training set to have a mean of 0 and a standard deviation of 1. And what this tells us is that one batch out of that training set, 512 elements, already does a pretty good job of having it sticks to that mean and standard deviation that we already know. In other words, the whole data set has a mean of 0 and standard deviation of 1. And what we find is that a batch of 512 also has a mean that's pretty close to 0 and a standard deviation that's pretty close to 1. All right, so P, he defines P as the first layer of the model applied to X. So we're looking at the mean of the weights of the first layer of weights. And the mean and standard deviation of X. So we've got the mean of 0.2 and a standard deviation of 0.3. And remember, that's not ideal. We would like to have the mean close to 0, the standard deviation close to 1. That's what we're going to address in the next notebook, the 07 notebook. Okay. Now he's going to go through for all the layers in the model. If the layer is a sequential layer, we're going to do the timing normal initiation. And we're going to set the biases to 0. So that's that. And now we can check again the mean and standard deviation. And, well, what happened? The mean is now close to 1/2, and the standard deviation is closer to 1, which is sort of good. Okay, now we have an enter and exit method. We can use it as a context manager. I'm going to have to look up what that means. I'm not sure what that means. It says that once we're out of the with block, all the hooks have been removed and aren't there to pollute our memory. All right, that makes sense. So this context manager thing, I think that's what this with as structure is. So it says with hooks model as hooks, we run the model, we generate the plot, we plot. On that plot, we plunk down each of the layers that we're interested in, the hooks from each of the layers. Then we put the legend on the plot. Then we make a second plot for this. What's the second plot for? Subplots 1, 2, 6, 5, 10, 4. What's different? MSSSH.stats, X0. Oh, X0 plot MS. Oh, so this is the first 10. The first plot we expect is going to be the first 10. And the second plot, so that's a zoom in at the beginning of the training. And the second plot is going to give you everything. And that's what we're going to do. So here we go. So this is now, we're now running the model and we're automatically outputting the plots. Let's do that. There it does. It's done the training for 2 epochs like we asked it to. We're now up to 69% accuracy. And now it's showing us the first 10 iterations. It's showing us the mean and the standard deviation of the first 10 iterations in these 2 plots. And so you can see that the mean starts out close to 0, but it's very unstable. And the standard deviation starts out relatively close to 1, but it's also very unstable, even in the first 10 iterations. And now you can see over the entire training that the mean is pretty unstable. It's meandering away from 1, especially away from 0, especially for the blue, which is the first layer. The blue, what is the blue? What is the first layer? I think it's just the transformation from the vector to an array, if I'm not mistaken. Let's go back up and look at it, where it prints out all the layers. Here we go. No, the first layer is not what I said it was. It's the first convolution. So it's the 5x5 convolution with the 2 padding and followed by the ReLU. So for some reason, that layer is very unstable in the mean and in the mean here. In other words, the mean starts close to 0, and all of a sudden it spikes up to 1, and then it stays level there.
And the possible reason could be because the weights are random, and then maybe after first layer, due to the SGD, the weights are getting stabilized a bit.
They're certainly stabilized. That's right. But they're stabilized at 1, and I think at this point we don't much care what the mean is. We're really more interested in the standard deviation being 1, being close to 1. And clearly that's happening for some layers, but not for others. So it looks like the deeper you go, it's not quite, but the first layers are, the standard deviation is stable close to 1. That is the blue layer and the yellow layer, and the green, even the green layer. It's stable all through the whole training process. It's stable. The standard deviation is close to 1. But then the third layer and the third layer, it starts to go a little bit wild. And the fourth layer, which is this pink, it gets really wild. It goes up to 4. And the fifth layer, well, the fifth layer is stable again. But let's go up and see what the fifth layer is again. I think the fifth layer is just this average pooling layer. So it's not surprising that that's more stable. The fifth layer is the adaptive average pool, and that's averaging a lot of stuff together. So it's not surprising that that's more stable than the other one. But anyway, it's still not ideal behavior. So now he's defining this.
Joseph, could you clarify what exactly we're plotting here? Are we plotting the?
Oh yeah, okay, that's what I was saying here.
Mean and standard deviation of the outputs as we're training, or something else?
Yeah, we're plotting the mean and standard deviations of the weights.
Of the weights, not the outputs.
Well, the weights are the outputs of the layers. In other words, these different layers are the sequential layers in our, they're the CNN, they're the convolutional neural networks layers, and the last one is the average pooling layer.
Right. So it's the state of the layer as opposed to the output of the layers on the input data, right? I'm trying to figure out what's being plotted here.
Yeah, that's a good question. And I believe what's being plotted is the mean and standard deviation. The left one is the mean, and the right one is the standard deviation. See X0 plot MS and X1 plot SS. So mean, standard deviation. He didn't label the plots. It could have been better. It takes a little more effort to label them, but this is fine. What he's plotting here is the mean of the outputs of these layers, right? So what comes out of layer 0, the mean of that, of all the parameters, which are the weights that come out of layer 0, after the ReLU has been applied. Does that make sense?
It's uncapped, right, ReLU?
Pardon?
Uncapped.
Yes. Remember, at the end of every one of these layers, there's a ReLU. If we go back up to these layers, there's a list of them. And we can see that every one of these things is followed by a ReLU. So it is the capitalized, it's the actual ReLU function that we're using. Okay. So it's the output of the layers, I believe, that is what we are, that we're taking the mean and standard deviation of after the ReLU has been applied. That's my understanding of it. Okay, where were we? We were down here, context manager, blah, blah, blah. Okay, so now we're running the model in a new way now. It's automatically generating all the plots that we want, which is kind of really cool. And so remember, you were asking about the plots. Mean and standard deviation of the first 10 iterations, that's the first row. And the second row is the mean and standard deviation of the whole thing. So basically, this is a zoom in on the first 10 iterations of this. And you can sort of see the features. This spiky thing here is this. Okay, it's just, this is a zoom in towards the beginning of the training. And this is the entire training, right? So what do we see? We see that the mean at least stays, it's not going crazy. It's staying between 0 and 1, which is good. It's not going down to 100,000 or 10 to the 5th or whatever. So that's good. The standard deviation is also relatively well behaved. I mean, it's only going up to a maximum of 4, so it's not terrible. And in fact, at the last layer, after the average pooling, it goes back down to 1. So I guess that's a good thing. So I think the timing initialization is doing what it's supposed to do, which is to keep, at least its goal is to keep the standard deviation close to 1. All right, so now he's building this function called append stats, and it has an input as a hook, a model, an input and an output. And if not, has attribute hook stats. So if the hook doesn't have a stats attribute, then we initialize stats to a tuple of 3 empty things, okay? Means, standard, and these 3 things are means, standard deviations, and histograms. What's a histogram? A histogram is a plot of, we'll see in a minute what it is. The mean, standard deviations, and histograms is going to be populated by hook.stats. Then we're going to add the output from data.mean.cpu. We're going to append onto the means from the hook and the model and the input and the output. And we're going to append onto the standard deviations, and we're going to append onto the histogram list. And here we have output.data.cpu.histc. Histc is the histogram function, and it's going to these inputs. Let's take a look. Histc is not implemented on the GPU as the note here. So let's take a look at this thing. Insert cell below. Histc is a, we can also look this up in Python. It's a Python command, I believe, or maybe a PyTorch command. Oops, it's not found. Histc. Not defined. Okay, so why? Oh, so it's a method. It's a method on data. So let's see if we can take this. How about data? And data is a data bunch. So data bunch, data bunch dot histc. I'm trying to figure out what this is. Oh, I understand what it is, but I want to. Nope, it doesn't have that. Let me look it up because I believe it's in. I believe it's in Python. No, SciPy. Anyway, I believe what this does is it gives you a histogram with 40 bins, and the bins are spaced between 0 and 10. That's what this histc command does. So we'll execute this. There's a way to get a look at to get a definition of this histc function, but I don't know what it is right now. So, okay, then we put the model on. We run the model on CUDA, and we put the model on CUDA. We build the learn and the run objects with a learning rate of 0.9, and the callback list, the same one we had before. We're not changing the callback list from what we had before. So now we're all ready to actually do training. But first, we initialize with timing normal initialization. Timing normal underscore L, each layer dot, wait, I'm not sure what this is, but L 0 dot bias. And we're setting so each layer, we're setting the biases to be 0. And we're initializing the weights using timing normal initialization, which we covered in, I think, notebook 2, or somewhere back there. All right, so we've done that. And now we do this, we do the training using this, what he calls a context manager approach. And this is something good to look up with the with as structure in Python, because it's very useful. And I've noticed he uses it quite a lot. It's just, this isn't something specific to Fast.ai. This is something that's Pythonic, and we should learn it. So it would be good to go look this up on the Python language reference if you have a chance. anyway, so we're going to run the model now with our new append stats function. So we basically run the model, we've trained it up, and we've got an accuracy of 0.92. We did this on CUDA, but now we have this append stats we can get at all of the information that we gathered using the hooks. So we gathered all this information on the weights during the training using the hooks method, and now, okay, he's got this method return. Torch.stack, that's a PyTorch method. H.stats of 2. I'm not sure what that is. He's doing a chaining method here. .t is maybe, I'm not sure what that is. And then he converts it to float, and then he takes the log 1p. Log, I'm not sure what this is, but it's a chaining. We can look these things up. It's not rocket science. Okay. So he's defining this new histogram function, and now he's using the new histogram function. Or not yet, let's see. So this is how you set up a plot with you want a 2x2 plot, and you want the figure size to be 15 by 6. You can see it's long, 15 units by 6, 15 units long, that's the x direction, and 6 units high, that's the y direction. So this command here, it sets up a plot using matplotlib. I think people are familiar with this if you know Python. And now we are generating all the subplots. Axes.flatten, hooks up to 4. We just want the first 4, the first up through 3, 0, 1, 2, and 3. Imshow, get hist. So we're actually viewing the histograms using an image, because the histograms are going to be 2-dimensional. And so we might as well view them using the image of the imshow. And the origin is lower. That means the origin is going to be here. And axis off, I'm not sure what that does. Tight layout means put all 4 of these close together. So let's run that. And what are we plotting? We're plotting along this way is the bins of the weight bins. So this would be 0 weights, and this would be 1 is somewhere along the continuum here. And we're plotting, we're plotting mean and standard deviation, I think. So I'm not sure why. Oh, and there are 4 plots. No, we're not plotting mean and standard deviation. We're plotting the histograms for the weights for the 4 layers, okay? So this is the weight value along the x direction, and the y direction is the distribution of values. And so I think black, I'm not sure whether black means 0 or, you can see the continuum goes from black to yellow, and that tells you the value of the weights. So these are all the histograms. And now we can use the get min method. He built a method to get the minimum and the maximum. And he generates 2 more plots. Minimum for each of these 4 layers, we can look at the minimum in the histogram. And there they are. The minimums are all sort of near 1. Okay, now he wants to do this with a better ReLU function. Jeremy has this idea that he's got a better ReLU than the normal ReLU that people use. And so he wants to implement it here. General ReLU, it's going to be initialized. It's a leaky ReLU. It can be leaky if you put in a leak size. Sub, max v, I'm not sure what sub and max v are, but you can give those as inputs. It is a module, so it's a class that inherits from module. So when it initializes, you have to initialize it from module. And then you can input the leak, the sub, and the max v. So I'm not sure. Oh, the sub is what I think it's what you subtract from it. And the max value is, you give it some maximum that you want to allow it to have. So we'll see how he uses it. So this is all for export now. He's defining all of these functions that he wants to use later. And now he revamps the append stats function. It's basically doing the same thing, except now the histogram, because he's kind of subtracted the mean, I think. And so now instead of the bins running from 0 to 10, they run from -7 to 7. That's the difference in this function. So now he again generates the model, initializes it, gets the learner object and the runner object, and then using this context manager method, that is the with as function, the with as structure, he runs the model using these hooks, in other words, collecting all the data that we want from the hooks and plotting the data. So again, he's plotting the mean and the standard deviation for the first 10 epochs on the first row of plots, and the second row of plots is for the entire training. Okay, so we're going to do that, and we got up to 96% accuracy here. The means are fluctuating, but not wildly, right? I mean, the biggest fluctuation is 0.35 here, and the standard deviations are fluctuating again, but not wildly. They're actually staying close to 1. So this is the advantage of the Chi-Ming normalization. And now if we look at the entire training, again, the means are well behaved. They're not 0, but they're not going off into the wild blue yonder. They're staying well behaved. And the most important thing is that the last layer, the mean is actually the closest to 0. So I would say the means are pretty well behaved here. The standard deviations are, again, not what you would ideally want, which is 1, but on the other hand, they're not too far away from 1. Even 3 isn't terrible when you think they could be 10 to the 6th, you know. So the standard deviations and the means are well behaved here, I would say. And when we plot them using the histograms, we can see that there's a band. In other words, most of them are centered around 1. This must be 1, the value of the mean. Yellow must be 1. And, or maybe yellow is 0. Yellow must be 0. And so you see, and the best thing to do, when I go through and redo this one, I'm going to put axes on here, and we're going to clearly see what's being plotted and what the scales are. Because if you've ever worked in any context, industry or science, nobody is going to accept a plot like this. Your boss is going to say, what the hell is that? You know, give me the, you know, label the axes and tell me the color scale, show me the color scale, what's on the y-axis and what's on the x-axis, and what does each plot mean? So you want a title on each plot, you want an X label, you want a Y label, you want a color scale. And when I go through and redo these, I'm going to, or you can even do it yourself, you can actually do this and make the plots nicer in that they give you more readable information about what they're actually representing. But from what I'm understanding of these plots, they're showing us that the means and the standard deviations are relatively well behaved for these 4 layers. Okay. This is the get min function, and now we're going to plot the mins again. And now the mins, because he subtracted the mean from everything, the mins, remember the mins were close to 1 before, now they're closer to 0. So, so Jeremy's generalized ReLU is working in the sense that it's bringing the means closer to 0. Actually, the means, what are we seeing here? I think these are the means from the 4 layers that we're interested in, the 4 convolution layers. Okay, so now he wants to export this thing. And now we're going to build a schedule, remember from back on this, I think it was Notebook 5, Anil, something like that, where we built schedules. Building the schedule, we're going to build the runner and the learn object and the run object. And here, I believe that, okay, it takes the data. I think this is the number of epochs. This conv layer, not sure what this is. This is the callbacks function. And so notice what we're doing. We're adding to the, remember the callbacks function has to be, the callbacks has to be a list. We already have a list called CBFS. And so we're appending onto this list the parameter scheduler so that we can use our schedule that we just built. So this is the new learn and run objects. Now we can run it for 8 epochs. We're going to run the fit directly. And we see that the training is growing nicely, and it's the accuracy is growing, is approaching 98%, even with the validation. So things are working well here, you have to say. Remember, the first number here is the loss function, which starts out large. And remember, the loss function, we're trying to minimize it. So every time, every epoch, we're reducing that loss function. And we got it down to 0.077. And then the second number here is the accuracy. The way, and that's just the way this run function was defined way back when. It was defined to give us these two outputs. Okay, now he makes the observation that chiming uniform, when we studied chiming initialization, we studied normal initialization, which means initializing with a random Gaussian function. Remember, the Gaussian is the bell-shaped curve. But people have found in practice that the uniform distribution is better. So we're going to now use chiming uniform distribution, and that is this uniform equals true switch. He said that the normal distribution puts a lot of the weights near 0, and that makes sense because the normal distribution is peaked around 0. So a lot of the weights get to be 0, and that's not a good thing. So by using a uniform distribution, which is uniform between 0 and 1, we're spreading out the weights so that not so many of them are near 0. All right. So that's what we're doing here. And we're going to do the scheduling thing now, which is supposedly going to get us faster convergence. So let's, I think we saw that already. After 8 epochs, we're already up at 98%. I think I ran this, but no, I haven't run it yet. So let's run it again. And let's see, does it converge faster? And it appears like it's roughly the same. The behavior is roughly the same. I don't see much difference. All right, so now we're going to export the module. I think we're at the end here. And this is Stas Beckman's new function that allows us to export the notebook. We run this, and then so this is the definition of the notebook auto export function. And then we do this, and it exports the notebook in the form that we've just done. And now I'm going to save it. And that's the end of notebook 6. And it took us, Jesus, it took us 2 hours to get through it. That's just one notebook. I can't believe that Jeremy got through something like 6 of these notebooks in one 2-hour lecture. So this course is really compressed, and going through it in this study group fashion gives us a chance to uncompress it and go slow enough so that people can actually pick up at least a sense of what's going on. And then if you go through it on your own later on, you'll get a much better sense. I mean, watching me do this is great. I've slowed it down. I've tried to be able to answer questions and so on, but nothing substitutes when you get in there and get this notebook and run through it and play with it, whatever. When you run through it, you'll have ideas. How can I change it? What about this? What about that? You can, and the notebook is very plastic in that sense. You can do with it whatever you want. You can make it answer your questions. And that's what a learning session should be. When you sit down with a notebook, you should try to interrogate that notebook and make it answer your questions by putting extra command lines, extra print statements, and so on. That's how you work with these notebooks. And after you do this for a while, you'll find ways, every time you, at least this happens to me, whenever I'm working through somebody else's notebook, I'll always figure out ways to make it nicer in my sense of the word nice. So I'll just modify it till I like it. And you'll be doing that too when you go through these. You'll have a sense of what your aesthetic sense is. What would you like to see it look like? And then you'll modify it to make it nice in the way that you think nice means. Okay. So I think that's enough for today. Thank you for staying with me. All 10 of you are still here. And let me see if there are any questions. If you want, this is the time to ask questions before we leave. Any questions at all? All right. Okay, well, thanks for your attention, everyone, and we'll see you next week. We'll go through, I'll go through the tail end of this notebook for those that didn't stay, and then we'll definitely make it through notebook 7 at least next time, and maybe start, and hopefully we'll actually start chapter 11, all right? So you can listen to the videos and get yourself ready for that. All right, over and out. I'll see you next